So up until this point, we've been talking about enthalpy and entropy. And one assumption that we've been making is that if a reaction is exothermic, then it's going to be a spontaneous reaction, while if it's endothermic, then for the most part, you need to put energy into the system in order to get it going, and therefore it's going to be non-spontaneous. Similarly, we assumed that if entropy increases, that's going to be a spontaneous process, while if entropy decreases, that's going to be a non-spontaneous process. Well, it's not as simple as that. Instead, what we need to do in order to determine if a reaction is spontaneous or not is to actually calculate one more new variable, and that is your Gibbs free energy. Now, spontaneity depends, as we said, on both enthalpy and entropy. It's not one or the other. And so in order to compare these and determine if a reaction is spontaneous, we're going to calculate the Gibbs free energy, which is represented by delta G. So your delta G helps us to determine if a reaction will occur spontaneously. And so here's what you need to know. This formula right here relates enthalpy and entropy. Now, delta G, your Gibbs free energy, your standard Gibbs free energy, represented by that naught symbol, equals your enthalpy change, your standard enthalpy change, minus the temperature times your standard entropy change. Now, if delta G is negative, then what that tells you is that your reaction is spontaneous in the forward direction. So if you're given your enthalpy, you're given your entropy, and you calculate your Gibbs free energy, and the value you get, whatever it is, if it's negative, if it's less than 0, then your reaction is spontaneous. If it equals 0, then your reaction is in equilibrium. The concept of equilibrium you should have been introduced to in first year chemistry, the fact that the rate of the forward reaction equals the rate of the reverse reaction. We looked at that a tiny bit in kinetics. We're going to look at it even more in the next big idea. And then finally, if your delta G is positive, that means that the reaction is non-spontaneous in the forward direction, but in the reverse reaction, it is spontaneous. And so we can calculate your Gibbs free energy, your standard Gibbs free energy, in order to determine if a reaction is spontaneous or not. So enthalpy and entropy contribute in addition to temperature, and your Gibbs free energy is how you actually calculate if a reaction is spontaneous or not. So let's look at an example. Here it asks you to calculate your standard change in Gibbs free energy for a reaction for which your standard enthalpy change is 24.6 kilojoules and your standard entropy change is 132 joules per Kelvin at 298 Kelvin. And it says, is the reaction spontaneous under these conditions? Well, I'm going to use this equation. I'm calculating my delta G. I know my delta H is 24.6 kilojoules, but since it's kilojoules for enthalpy and joules for entropy, I'm going to convert the enthalpy kilojoules into joules really quickly by just multiplying by 1,000. So I end up with 24,600 joules minus my temperature, which is 298, times my entropy change, which is 132 joules per Kelvin. And so when I do that, the answer I get for my standard Gibbs free energy change is negative 14,736 joules. Well, since my Gibbs free energy is negative, that means that my reaction is spontaneous. Okay, so that's all there is to it. That equation allows you to relate enthalpy and entropy in order to determine if a reaction is spontaneous or not. So another way of calculating your change in Gibbs free energy for a reaction is by using the standard free energies of formation. Now, this equation should look extremely familiar to you. We did it for enthalpy changes, we did it for entropy changes, and now we're going to do it for Gibbs free energy. So let's look at an example. It asks you to use the data from Appendix C to calculate your standard change in Gibbs free energy at 298 for the combustion of methane. Okay? So your standard free energy change equals the standard free energy of formation of carbon dioxide, which is your product, plus the standard free energy of formation of water times 2, because there are 2 moles of water. And then I'm going to take those, add them together, and subtract the standard free energy of formation of oxygen times 2 plus the standard free energy of formation of methane. Okay? Now, the standard free energy change for this reaction equals, and well, I'm going to look up these values in Appendix C. For carbon dioxide, it's negative 394.4 kilojoules plus the standard free energy of formation of water, which is negative 228.57 times 2, minus, well, the standard free energy change of formation for an element in its standard state, just like with enthalpy, is going to be 0. So that of oxygen is going to be 0. Remember, for entropy it was not, but for enthalpy it was. Plus the standard free energy change of formation of methane, which is negative 50.8 kilojoules. And so when I calculate that, my standard free energy change for that reaction is going to be negative 800.7 kilojoules, which tells me that that reaction is going to be spontaneous. So let's relate free energy and temperature. Because we're given this equation, delta G equals delta H minus T delta S, what happens if delta H is negative? What happens if delta S is negative, et cetera, et cetera? So let's look at the very top and make sure we understand this. So if my delta H is negative and my delta S is positive, what that tells me is no matter what the value for my temperature, my delta G is going to be negative. Okay? If my delta H is positive and my delta S is negative, that tells me that my delta G is automatically going to be positive no matter what the temperature. Because remember, you're subtracting by temperature times your change in entropy. Now, if my delta H is negative, but my delta S is also negative, keep in mind now that your delta H and your delta S are going to be battling it out to see which one impacts your delta G the most. Okay, so since delta H is negative and delta S is negative, the smaller your temperature, the lower your temperature, the less of an impact your delta S will have on delta G. So as a result, if you have a low temperature, delta H, the negative value for delta H, is going to dictate a negative delta G. Now, if your temperature is high, what that means is that your entropy change is going to be dictating what sign your delta G is. And since it's going to be positive and larger than the negative value of your delta H, that means that your reaction is going to be non-spontaneous. In contrast, if your delta H is positive and your delta S is positive, well then if your temperature is very, very large, then that means that your delta G will be negative, meaning it's going to be spontaneous. But if you have a very low temperature, that means that your delta H is going to take over, which means that the equation is going to produce a positive delta G, and therefore your reaction is going to be non-spontaneous. So to find the critical temperature, and this is the temperature where delta G is going to go from being positive to negative or negative to positive, you have to set your delta G equal to 0 and then solve for your temperature. Okay? So let's look at an example to make sure we understand what I'm saying. So here it gives you your enthalpy change and your entropy change, and it asks you at what temperature will the reaction have a delta G that's equal to 0. Okay? So I'm going to write this equation. I'm going to set my standard free energy change equal to 0. I know my enthalpy change is negative 32 kilojoules minus, I don't know what the temperature is, but I'm going to multiply that by my entropy change. Notice I converted my entropy to kilojoules versus converting my enthalpy into joules. And I'm going to just solve for my temperature. So when I solve this, the temperature I get is 330 Kelvin. So let's look at this. At 330 Kelvin, my reaction is at equilibrium. Okay? So if I raise my temperature, so look right above, it's negative 32 minus T times negative 0.098, which makes this, the temperature times your entropy change, a positive value. So if my temperature increases, what that means is that's going to make my delta G positive if it goes above 330, because at 330 it makes it equal to 0. If I go above 330, that means that my delta G will be positive, meaning it's going to be non-spontaneous. Now, if I decreased my temperature, then that means that my enthalpy, the negative 32, would take control, and therefore my delta G would be negative, and therefore the reaction would be spontaneous. So you'll see questions in which it says, all right, what is your critical temperature at which your standard free energy equals 0. And then it says if you increase it, will the reaction be spontaneous? If you decrease it, will it be spontaneous? So just being comfortable recognizing the fact that whenever your standard free energy change is negative, then the reaction is spontaneous. If it's positive, it is not spontaneous.